recording. Okay. Is it sharing with you now?
No, sir.
No, sir.
No, it is, right?
Yes, sir.
How can I remove these photos, these images? Can anybody know?
So we are able to see only the blank screen, sir.
Okay. But can you see the pictures of the participants?
Your Zoom window will not be visible to others.
But when I am recording, I have seen that these pictures are coming in the middle of this presentation.
Use the dashboard answer. You can just minimize.
Sir,
all
on
of-
the top you have hide thumbnails, sir.
Okay.
On the top of those images.
On the top
You
of,
have different options.
Options, sir.
Single dash, single box, double.
yeah, single dash is also
Use
there.
the single dash, sir. It will minimize all the screen.
All the
But it is coming one of the participant thing, right?
Only single dash, sir. It will not give any participant.
you can move it to any
First
corner
option.
and
But okay. Whoever is speaking, their picture will come here then?
yes, sir.
Okay.
You can completely move it to the corner or just push inside the corner, sir. It will come.
Okay.
Push inside the corner.
I'm not sharing full screen so that it won't disturb. It is one. Okay. Anyway. So as we start a new method to handle nonlinear separable spaces. Separable, linearly separable means if there are two classes, if you can separate them with a line. I have described that when we were discussing about the logistic regression. So sometimes this may not be linearly separable. You can see here the data of two classes. The first one, you can draw a nice line between those two classes so that it separates. Down to that line is one class, above to that line is a different class. But if you come to the right side picture, then can you separate them with a line, greens and blues?
No, sir.
Whatever
No,
line
sir.
you take, you cannot. So these are called not linearly separable, but still you can separate with a circle, right? Inside of circle, outside of circle.
Yes.
There is a boundary between greens and the blues, but that is not a linear boundary. That is called non-linear boundary. So how to capture these non-linear boundaries? That is the question. If you want to separate with a line, then definitely it will give non-accurate results. So we need to get non-linear boundaries. So circle means you know that it's if you allow quadratic polynomials, then you will get a circle, because circle equation is x minus x1 whole square plus y minus y1 whole square equal to r square. Do you remember circle equation?
Yes, sir.
x1, y1 and radius r. So, but in linear hypothesis, we don't allow to go for more than one polynomials. Means only the term itself, no powers. So now we will see that it's But how do we know that it is enough to go only up to second degree polynomial, third degree polynomial, fourth degree polynomial? That is a big problem now. See, if it is, if we need to take, whether we need to take in multi-regression, multivariable regression, whether x square or x1 square, x2 square also, it's many things will come, whether to take x1, x2, that is also second degree term if you cross multiply the variables. So for that, we need to think, how do we handle that? So here, the new concept comes that is called neural networks. So how do we represent neural networks? We'll see. So neural networks for non-linear hypothesis. So we don't assume now only linear terms will be there in our hypothesis. We will also allow non-linear terms. Performing linear regression with a complex set of data with many features is very unwieldy. We'll take some examples. If you want to exhaust all non-linear hypotheses, is it easy for us? Suppose you want to create a hypothesis from 3 features that included all the quadratic terms. So if you have 3 features, what are through those 3 features? X1, X2, X3. How many ways you can form second order terms? Quadratic means second order terms. So how many ways you can form second order terms from 3 features? 3C2. Do you agree that formula?
Yes, sir.
Yes, sir.
Because out of 3, any 2 you can take, right? And it can also be repeated. They don't need to be distinct. Means x1 square is also possible, right? So it is allowed repeatedly. So it is not 3C2. What is it then? The 3C2 will give you only 3. In 3C2, once x1 is selected, you cannot select again x1, right? The first one can be taken, any one of these 3, x1, x2, x3. Am I right?
Yes.
Second one also can be taken any x1, x2, x3. So first one, how many ways you can select? 3 ways. Second one, how many ways you can select?
3 ways.
3 ways. 9 will come, right? But we have only 6. Then how is it possible?
Repetition is repetition not allowed?
So we will remove those repetitions.
Yes.
First one x1, second one x1. That will repeat 2 times actually. Okay. So repetitions you will remove. So once you remove repetitions, you can get 6. So here x1 square is 1 term, x2 square, x3 square. Then cross is x1, x2, x1, x3, x2, x3. So these many with 3 features itself, you need to do these many. If we increase the features, only for quadratic we are looking. The exact way to calculate how many features for all polynomial terms is the combination function with repetition. That is what we did. That formula is n plus r minus 1 factorial by r factorial n minus 1 factorial. Anybody is interested in aptitude? This is an important formula. Combinations with repetitions. Without repetitions, what is this formula? Simply NCR, right? NCR
Yes.
equal to, what is formula for NCR?
N factorial into r factorial, n factorial by r factorial into n minus r factorial.
Okay. So this is the repetition formula. You can use this formula to get that. For 100 features, if we wanted to make them quadratic, we would get 5050 resulting new features only for second order terms. Remember, if you want to introduce nonlinear terms up to second order, then we need to, our multi variable regression will become with 5050 variables, means that many columns will come. So it becomes more complex now. You may not have that many data points, but you will have that many features. Whenever you have less data points, then it will become overfitting, remember, than the number of features. You understand what I'm saying? If number of features are more than the number of data points, or instances, it leads to what? Overfitting. So it nicely fits because you have more variables to vary, but less number of things to fit into that. So nicely you can fit, but whenever new data comes, then it won't perform well because it has become more suitable only for that data set. It lost the generality. That is the problem when you have less number of instances, but more number of features. So that problem also will come here. The number of features will increase, but instances won't increase. So we can approximate the growth of the number of new features we get with all quadratic terms with order of n square by 2. And if you wanted to include all cubic terms in your hypothesis, the features would grow asymptotically at order of n cube. So if third means n cube, then these are very steep growths. So as the number of 4 features increase, the number of quadratic or cubic features increase very rapidly and becomes quickly impractical. So here another example we'll take. Let the training set be a collection of 50 by 50 pixel black and white photographs to classify which ones are photos of cars. The feature set size is then n equal to 2500. If we compare every pair of pixels, now let's say we need to make a quadratic hypothesis function with quadratic features. Our growth is order of n square by 2. So our total features will be about, how much this is? 31,25,000, which is very impractical. You may not have that many pictures also, photographs. So it is impractical, and we don't know that whether they really contribute or not. We are just assuming after building the your weights, finding weights, then only will come to know that it see which features have got weights which are not close to 0. They only will contribute. But before that, you need to do your fitting with these many features. That is impractical. So neural networks.
Sir.
Yes.
Sir, in the previous example, how can the features be 31 lakhs, sir? Because for we can consider every pixel as a feature. So it will be either black or white.
Yeah, 50 by 50 pixels photograph.
Yes, sir. In that case, there will be 2500 pixels, right, sir?
2500 pixels are there.
Yes, sir.
Each pixel is x1, x2, x2500 now. Each pixel, the light intensity will become one column.
Okay.
So 2500 columns will come, means x1 dash 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 to x2500. So if you want to take linear hypothesis, then 2500 are good enough. But if you want to extend to the quadratic, then for each pixel, you need to take the quadratic terms. Those are 2500 and cross terms also. All those put together, it becomes 31 lakhs.
Okay, sir.
So neural networks offers an alternate way to perform machine learning when we have complex hypotheses with many features. So some analogy is given here how brain works. Neural networks are limited imitations of how our own brain works. They have had a big recent resurgence because of advances in computer hardware. So usually it's how we do all these computations when you go and study brain, there are so many connections inside. So then there is some trigger, that neuron fires, then it releases something that goes to another network. Then again, it fires some neuron. Fires means it will take some signal and output some signal like that. If you are interested, you can go and see that some of the online material, how neurons and brain are close when building neural networks, the idea. But later on, people gave up that idea of exactly mimicking how a human brain works. Instead of that, they tried more to the computing side level. But initially, the idea come from the how brain works. People want to imitate that. There is evidence that the brain uses only one learning algorithm for all its different functions. This is again biological people. They gave this hypothesis, and they're almost there to prove that. Scientists have tried cutting in an animal brain the connection between the ears and the auditory cortex and rewiring the optical nerve with the auditory cortex to find the auditory cortex literally learns to see. So is there different learning functions for different things, ears, nose, eyes, like that, you'd see? Then they try to change those cortex from ear to nose, nose to ear. Then will it learn the same thing, smell and all those things? That is what they did, scientists. This principle is called neuroplasticity and has many examples and experimental evidence that they use only one learning function, whether it is a coming signal from nose, coming signal from ears, whatever that it's see. That is what they established, that there is only one form of the learning function. So model representation 1, at a very simple level, neurons are basically computational units that take input, dendrites as electrical input called spikes that are channeled to output axons. In our model, our dendrites are like the input features, x1 dash 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 xn, and the output is the result of our hypothesis function. In this model, our x0 input node is sometimes called the bias unit. X0 means your constant term. It is always equal to 1. X0 is always equal to 1, if you remember, right, in linear regression also. In neural networks, we use the same logistic function as in classification, 1 by 1 plus e power minus theta transpose x. This is 1 by 1 plus e power minus z, where z equal to theta transpose x. So we will use the same logistic function. In neural networks, however, we sometimes call it a sigmoid activation function. Sigmoid is nothing but the curve, is called sigmoid curve, that is, let's see. It slowly increases, suddenly it jumps to the other side, then slowly increases there. That is sigmoid function, like a S-curve. So our theta parameters are sometimes instead called weights in the neural networks model. Visually, a simplistic representation looks like x0, x1, x2. These are the initial features. Then you will add some more nonlinear features. Then finally, you'll get some hypothesis function h theta x. So our input nodes, layer 1, go into another node, layer 2, and our output as the hypothesis function. So earlier we were computing linear regression, logistic regression, inputs to outputs directly. Now we will come into the different functions we will take. First one layer, then those inputs are converted into different outputs, but that is not the final output. That will become input to the next layer. Next layer also will compute something by some functionality. Like that, it will go layers by layers. So our input nodes, layer 1, go into another node, layer 2, and our output as the hypothesis function. The first layer is called the input layer, and the final layer, the output layer, which gives the final value computed to the hypothesis. When we see it becomes more close, more clear, we can have intermediate layers of nodes between the input and output layers called the hidden layers. So you see the right side networks, input layer, some values, whatever input we get, x1, x2, xn. Then again, it will output as many as you want. This is not fixed. How many units are there or how many features you are generating from the 4 input features. Here in this case, 5, if you want 100 also you can generate. So these 5 again generates another set of features. Here in this case, we are generating 7. So these middle layers are called hidden layers. They're also called black layers. We don't understand exactly how. We only fix that and say, okay, you give 7 outputs, 8 outputs. By looking at the results, then we will play with these hidden layers. How many units should be given, those things. So neural network picture looks like that. So it is not having like only 2 layers, input layer, output layer, like in the earlier case of linear regression or logistic regression. We are introducing many layers between input and output. The middle layers are called hidden layers. So hidden layer 1, hidden layer 2. The number of hidden units in each layer are not fixed. That is again user input. So here you can see that it's because you are computing the hidden layer 1 features from the previous features. So how are you computing? You don't know exactly, but they are combinations of previous layer inputs. So you may be multiplying the same itself. You see the signal is coming from first one to first one, but you are also sending signal to all other units also. Means it is combination. So linear means without combination. Non-linear means with combination. If you are creating a new feature, that is called non-linear. So you are creating non-linear features in the second layer. Similarly, from those non-linear, again, you are creating more non-linear features from the previous layer, like that, it's see. So you are creating non-linear features from the input layer. So that is the essence here, because you are computing new features, combination of the earlier features. So that brings the non-linearity. So layers in artificial neural networks. So layer 1, this is your inputs, L1, L2, L3. Then these are weights you are assigning here. After weights, you are computing new features. So those new features, layer 2, it is generating new features here. Then again, you are generating from the layer 2 to layer 3 features. Finally, you will generate output. Output, if you want only 2, then you fix output units only 2. So you can fix the input layer, because how many features you have in the beginning, that is fixed. Input layer units are fixed, and output layers are also fixed. How many classes you have, that many you will get as output units. But in the middle, it is a combination of previous layer previous layer inputs. So it may be any number. That is the again user input. We label these intermediate or hidden layer nodes as AIJ and call them activation units. So we call these things as AIJ. So we'll see that how we need to understand this superscripts and subscripts. So AIJ is activation of unit I in layer J. So this superscript is in which layer this is, and subscript is of which unit, from which unit you are getting. So AIJ is activation of unit I in layer J. So here 3 are there. That's why you can write this is layer, hidden layer 1. So A12, A22 layer is this superscript. So this won't change. 2 will not change in the layer. This is layer 2. So hidden units, how many units you have? Here 3 units. So you write A1, A2, A3. So A12, A22, A32, A32. Similarly, it is third layer. 3 is fixed superscript for this. 4 units are there. That's why you are getting A1, A2, A3, A4 with superscript 3. And this is A14, only 2 units are there, A1, A2 in the fourth layer. So you are writing this as a 4. So we are counting here layers with 1, not with 0, like in Python arrays. So index will start with layer 1. Okay. So here you can see 3 inputs we are taking, x1, x2, x3. Give me a second. I need to take this urgent call. So what I do is I'll give you 5 minutes break so that I need to sign some papers, this MSIT papers. He has come from office.
Okay, sir.
I'll be back after 5-10 minutes. So you can stay back or you can rejoin. No problems. Okay. So I'm back. Can we continue?
Yes, sir.
Yes, sir.
So here you can see that there are 3 inputs are given. From that we are getting some hypothesis function. So what is these 3 inputs, x1, x2, x3? As usual, x not equal to 1. Our weights initially, our weights are theta naught, theta 1, theta 2, theta 3. So this is a sigmoid logistic activation function. That is what we take. So you can see here neurons analogous to neurons of the body. So all these neurons are coming together, they are bringing signal, and this will compute something out of that. Then again, it will give some output. So here you see you need to get 3 more output units. These are non-linear units. Initially they are linear units, x1, x2, x3. So how are you computing? We don't know still. We'll see that we don't say that it is quadratic term or third order term, whatever that it's. You compute something by getting signal from x1, x2, x3. So three different ways it computes from 3 previous inputs. So A1, 2 is computed with x1, x2, x3. Similarly, A2 is a combination of some x1, x2, x3. They may be additions, they may be multiplications, whatever, but it is computed from the many input features of the previous layer. Not directly it is getting a signal only with only one input variable. So this is layer 1, layer 2, layer 3. We will see that how do we need to assign weights now. Okay. Aij is activation of unit I in layer J. This is second layer activation unit A1. So how A1 is computed is, so to get A1, you will use the same linear regression hypothesis. But A1 is computed. Earlier, only one output was there, right, in linear regression. So you are computing only one A1 there. That is output, and whatever you get value, that you give as a output value. Now A1 is computed from x1, x2, x3. We will use the same hypothesis here. There we were using theta 1. Here because it's many thetas are involved here. So that's why we are getting a new notation. So if you think simply, theta 1 x naught, theta 2 x1, theta naught x naught, theta 1 x1, theta 2 x2, theta 3 x3. That's why you need to understand here. So this A1 is computed from previous 3 units. So previous 3 units plus 1 bias unit, that is x naught. Usually x naught equal to 1. So first you are computing theta naught x naught. Forget about this 1, all those things. So you take in the subscript only the second part. Theta 0 x0, theta 1 x1, theta 2 x2, theta 3 x3. Here also theta 0 x0, theta 1 x1, theta 2 x2, theta 3 x3, like that it's. But what are these weights? So we are saying that theta 101 means here you see theta j, matrix of weights controlling function mapping from layer j to layer j plus 1. So this theta 10 means it is coming from the 0th unit. Here we haven't depicted that 1. You may put 1 also here. From 0th unit, from layer 1 to you are getting 1 again here. So this 1 is the layer 1 units. 1, 1, 1, 1, whatever superscript is as there. So you are getting a weight. So you need to attach now weights for this A1 to weight of x1, weight of x2, weight of x3. So weight of x1 is theta 11. Weight of, for this particular layer, theta 1, means from first layer it is coming, these weights, from first layer to second layer. To the x1 means to unit 1. So 11, 12, 13. So the second subscript is the unit number in the previous layer. and this is the unit layer. And to which unit, which layer you are getting this. So if network has Sj units in layer J, Sj plus 1 units in layer J plus 1, then theta j will be of dimension Sj plus 1 cross Sj plus 1. So for A1 you need 3 weights, x1 weight, x2 weight, x3. Then A2 you need 3 weights, and A3 also you need 3 weights. Not only 3, why this plus 1 is coming? Any guess? The constant term is coming, right? X naught. X naught we haven't depicted here. You can also depict here x naught as 1. Then that also will give inputs. So then for each one you need, for A1 you need 4 weights from the previous units. For A2 also you need 4 weights. A3 also you need 4 weights. So how many weights you want? 4 by 3 or 3 by 4. Here in this notation, it is 3 by 4. So you see that all thetas you put, you will get exactly 3 by 4 matrix here. So that is what here it is said. Sj plus 1 multiplied cross Sj of plus 1. This dimension is. Sj is the unit.
I guess anyone of your
Okay. Here Sj is the number of units in layer J. When you go to the next layer, number of units plus 1 more will come, right? That bias. That's why this is Sj plus 1. So that many weights we need to find out by using same linear regression or sigmoid function. So this is saying that we compute our activation nodes by using 3 by 4 matrix of parameters. We apply each row of the parameters to our inputs to obtain the value for one activation node. Our hypothesis output is the logistic function applied to the sum of the values of our activation nodes. First, we'll compute theta 1, x1, theta 2, x2. Then we are applying the sigmoid because we always want that signal is between 0 and 1. So to the sum of the values of our activation nodes, which have been multiplied by yet another parameter matrix theta 2 containing the weights for our second layer of nodes. So each layer gets its own matrix of weights. The dimension of these matrices of weights is determined as follows. If network has Sj units in layer J and Sj plus 1 units in layer J plus 1, then theta j will be of dimension Sj plus 1 by Sj plus 1. The plus 1 comes from the addition in theta j of the bias nodes x naught and theta naught j. In other words, the output nodes will not include the bias nodes while the inputs will. So you don't generate any bias node in outputs. Only inputs will provide one bias node to compute the outputs. So only at the input layer only you can add this bias node. So if layer 1 has 2 input nodes and layer 2 has 4 activation nodes, dimension of theta 1 is going to be 4 by 3 because 4, 2 plus 1, 4 by 3, where Sj equal to 2 and Sj plus 1 equal to 4. So Sj plus 1 by Sj plus 1 equal to 4 by 3 matrix you'll get. So I want you to understand this carefully. Here, what matrix you are getting, you see, if you take the theta matrix of the layer 1, you are getting 3 by 4 matrix. Because Sj plus 1 means jth layer. First layer, how many units you have? 3 units. 3 by previous layer units plus 1. That is previous units here, 3 units plus 1 is 4. So 3 by 4 matrix you are getting. So total 12 weights you need to fit for this prediction or whatever that it's a classification. So first you will compute theta 1, theta naught, x naught, theta 1, x1 like that. Then you apply this sigmoid. So because there are 12 weights from layer to another layer, that's why this notation is coming. Theta 1, 0, 1, then theta 1, 1, theta 1, 2, theta 1, 3 from this is layer 1 weights. From 1 0 1 1 1 2 1 3. Similarly 2 0 2 1 2 2 2 3. This is unit 1 weights coming from previous layer unit 0, unit 1 weight coming from previous layer unit 1. This second subscript is denotes weight is coming from which unit in the previous layer. Then first subscript is for which unit you are getting this weight in the present layer. So 1 0 1 1 means 1 is fixed, means for first unit in this layer, in which layer we are computing weights, for first unit this is you are getting, so this 1 is fixed. Similarly for second unit you are getting these weights, this is fixed in layer 1. Similarly third unit in layer 1, that is fixed, but these weights are getting 0 means from 0th unit in the previous layer, 1 means 3 1 means 1 previous unit, previous layer, first unit, you are getting this weight to the present layer, third unit. So that is what we need to understand this notation here. So how do we compute these weights now? So forward propagation, vectorized implementation. So what we do is, now we got A12 is computed from the x1, x2, x3, like your linear regression hypothesis function, then applied the sigmoid, then whatever value you get, that will become A12. Similarly, A22, A32. Then you have this x, you represent as x0, x1, x2, x3. Then Z2, Z is nothing but after converting this, whatever linear regression will come, that will be written as Z. Z2 is Z12, Z22, Z32. This G of this is Z12, G of this is Z22, like that. See whatever is there in the brackets. Then Z2 is theta 1 of X. Because this is matrix theta 1 0 1 theta 1 1 1 theta 1 2. This matrix, if you write separately, if you multiply with x, x0, x1, x2, x3, exactly you'll get this thing here. Theta 1 0 x0, theta 1 1 x1. That is what you get when you write as a matrix multiplication. So Z2 equal to theta 1 of x. Then if you apply this logistic G function, that will become your final output for the second layer. That is not the output, final output of the entire network. Only first layer output to the second layer is A2. That A2 is G of Z2. First you compute theta 1 of x, then apply this G function, sigmoid function, then you will get A2s. So second layer variables will get, again this will become, second layer variables will become inputs to the third layer. So denote x equal to AJ. Okay, so this again, let's say you can write this as a input to the next layer. That's why you can denote x as AJ. So add A02 equal to 1. So when you are computing the next layers, you need bias unit. Always you write A02 as 1. Similarly, x0 equal to 1. Here, second layer units we are representing with A's. So A0 will become 1. So Z3 is theta 2 A2. Then H theta x equal to A3. That is G of Z3. So these are the third layer outputs. So your hypothesis H theta x, like in logistic regression, you apply sigmoid for what you got theta 1 x1, theta 2 x2, then get this A3s. Okay. So model representation, A12 equal to G of Z12. Z1 is computed like theta 1 x1 plus theta 2 x2, like that. Then G is the sigmoid function. Then you are getting second layer units here. In other words, for layer J equal to 2 and node K, the variable Z will be ZK2 equal to theta K01 x0, theta K1 x1. Similarly, let's say the same hypothesis function which we used for linear regression. First we use that, then apply the sigmoid. The vector representation of x is x equal to this x0, x1, xn, zj equal to z1j, z2j, znj. then setting x equal to a1, we can rewrite the okay. So when we can write the equation as zj equal to theta of j minus 1 aj minus 1, because we converted x2 as now a's, because we want to write the same equation for all layers. So not to confuse with x. So the first layer x0, x1, xn will become your a0th layer. So theta of j minus 1, a of j minus 1 we will write. So this next layer weights or next layer activation units are computed from the previous layer activation units. So we are multiplying our matrix theta of j minus 1 with the dimensions sj by n plus 1, where s is the number of our activation nodes by our vector aj minus 1 with the height n plus 1, because the bias unit is coming as 1. This gives us our vector zj with the height sj. Now we can get a vector of our activation nodes for layer j as follows. So ai equal to gzj, where our function g can be applied element wise to our vector zj. So when you write as a matrix, you need to apply that matrix function g on matrix. For each element, you need to compute that sigmoid value of the existing value. So we can then add a bias unit equal to 1 to layer j after we have computed aj. This will be element a0j and will be equal to 1. To compute our final hypothesis, let's first compute another z vector, zj plus 1 equal to theta j aj. aj is nothing but previous layer activation units. We get this final z vector by multiplying the next theta matrix after theta j minus 1 with the values of all the activation nodes we just got. This last theta matrix theta j will have only one row, so that our result is a single number. We then get our final result with h theta x is equal to aj plus 1 of g of zj plus 1. So if you want a single number, you need only one layer, one row. So that's why this last theta matrix theta j will have only one row, so that our result is a single number. We then get our final result with simply applying that sigmoid for that computed whatever from that single row matrix. So notice that in this last step between layer j and layer j plus 1, we are doing exactly the same thing as we did in logistic regression. So adding all these intermediate layers in neural networks allows us to more elegantly produce interesting and more complex nonlinear hypotheses. So if you go back and say why we are getting last layer, we are not getting any nonlinear things. If you see your last layer, how are you getting? All three are producing only one h theta x, right? A1 to A2 to A3 to, they are not producing more than one output here. So last layer will be always just a row, single row. But previous layers, you see that it's combinations are there. That's why you are getting a matrix here, not single row. But last layer will become single row to get the hypothesis function. So from this hypothesis, you will compute. Then you will say that it's whether this belongs to this class based on that probability, if it is a binary classification. Of course, we are discussing only binary classification here. So that's why here he describes the last layer will have only one row. Notice that in this last step between layer j and layer j plus 1, we are doing exactly the same thing as we did in logistic regression. Adding all these intermediate layers in neural networks allows us to more elegantly produce interesting and more complex nonlinear hypotheses. So we allowed them to interact and produce new signals. That's why it has become nonlinear now. Simple example of applying neural networks is by predicting x1 and x2, which is the logical and operator and is only true if both x1 and x2 are 1. So we take one example and see that how do we build a network for a known problem. So known problem is if two inputs are given, x1 and x2, when you apply AND between x1 and x2, so what is the truth table for x1 and x2? So it will result. Yes.
Both inputs should be positive for the result to be positive.
Right. And even if one is not positive, it becomes negative, right? So that is what how we get the network. We'll see. Graph of our function will look like x0, x1, x2 because x0 is your bias term. The two inputs x1, x2. Then you apply your neural networks, whatever that. But you should be able to predict based on these inputs. If both are true, then you should get true, this hypothesis. If both are false, it should get false. In all other cases, it should get false or negative. So remember that x0 is our bias variable and is always 1. Let's see our first theta matrix. Theta 1 equal to. So we need to get now weights. So we will take some weights now. Theta 1 equal to minus 30, 20, and 20. 3 weights because 3 are there. So this will give minus 30 x0 plus 20 x1 plus 20 x2 like that. This will cause the output of our hypothesis to only be positive if both x and x2 are 1. In other words, if your inputs are only 0 or 1, suppose, then if you take these weights, minus 30, 20, 20. So if it is to mimic the AND gate, then it should be true or it should become non-zero value, 1. Only in the case of the both x1 and x2 are 1s. So you take now, what will happen? Minus 30 x0 plus 20 x1 plus 20 x2. Even if 1 is 0 out of x1 and x2, what will happen here? Minus 30, remaining things are 1s, only 1 is, remaining things are 0, only 1 is the 1. Only 2 are there. 1 is 0, like that. It's if you see here, x1 equal to 0 and x2 equal to 0, right side if you see, then g of minus 30. You are getting after computing minus 30 plus x1 is 0 anyway, this is 0, x2 equal to 1, x2 is also 0, then you are getting minus 30, it is less than 0, so it will produce 0. Similarly, when x2 equal to 1, minus 30 plus 20 will come minus 10, then also it is 0. For other case also it is 0. Only in the case of both the x1 and x2 are 1, then only it becomes positive. So then we can predict this as a 1. So you are able to build a network for this x1 and x2 functionality. People also call these perceptrons sometimes. So don't confuse with the words. This is also called perceptron means not many layers, only one layer is there. They are called perceptrons. But they are nonlinear computations here. So we have constructed, why we are writing here G? Again, if you apply this G, then if it is more than 0, it produces 0.5, less than 0, it produces less than, right? So that's why the sigmoid function is making sure that only it will become more than 0, provided it is greater than, if it is, then only you'll get 1. So that's why here still that sigmoid is applied. For the notation of sigmoid, they are writing Z. So we have constructed one of the fundamental operations in computers by using a small neural network rather than using an actual AND gate. Neural networks can also be used to simulate all other logic gates. There are examples you can see. You can build neural networks for all other gates also. Okay, here AND gate is written minus 30, 20, 20. NOR gate is 10, minus 20, minus 20. And OR gate, you need weights, minus 10, 20, 20. So OR is easy, right? Even if one becomes non-zero, then it should get positive. So this minus 10 is the bias. Bias will see that if both are zeros, then only it becomes minus. Otherwise, even if one is non-zero, it becomes positive, you'll get positive. So NOR, only two weights will require here. Minus 20 minus A means minus 20, minus will become positive. That's why this will work as an OR. We can combine these to get the XNOR logical operator, which gives 1 if x1 and x2 are both 0 or both 1. So then you can take x0, x1, x2, then combine this with these a1 to a2, then get a3 h theta x, which should work for XNOR. What should be weights for these this network? There are two layers, so two layers from first layer to second layer to third layer. So two sets of weights you require. First sets of weights is minus 30, 20, 20. Second layer weights are 10, minus 20, 20, minus 20. You apply this and see for the transition between the second and third layer, we will use a theta2 matrix that uses the value for OR. So you are combining now XNOR means and OR. Then you are getting XNOR. Minus 30, 20, 20 are your AND gate weights, and NOR gate weights are 10, minus 20, minus 20. If you put together AND and NOR, then you are getting XNOR. So let's write out the values for all our nodes. A2 equal to G of theta 1 multiplied by X. A3 equal to G of theta 2 multiplied by A2. Then H theta X equal to A3. And there we have the XNOR operator using two hidden layers. In fact, only one hidden layer here. It should be corrected. Only one hidden layer. This is the hidden layer. A1 to A2 is. So this is the example of how neural networks can be used to build nonlinear hypothesis. Because if you see this 0, 0 matrix, if you put them here on the space 0, 0, 0, 1, 1, 0, 1, 1, these are the corners of a square, right? Can you put them with any line separating ones one side and zeros other side? It is not possible. So that's why we need nonlinear hypothesis. So that is what we try to understand here. Nonlinear things can be computed through neural networks. So in multi-class classification, what we do to classify data into multiple classes, we let our hypothesis function return a vector of values. Instead of only one hypothesis, we will give a vector of values h theta x1, h theta x2, h theta x3, h theta x4. Say we wanted to classify our data into one of 4 final resulting classes. Then our final layer of nodes, when multiplied by its theta matrix, will result in another vector on which we will apply the G logistic function to get a vector of hypothesis values. So at a time you will get 4 hypothesis function based on this. Then again you will get weights. So only one will become always non-zero, or remaining things all will become 0. So wherever position you get a non-zero value or one value, the prediction will become that particular class. So if you see here, the predictions will become h theta x equal to 0, 0, 1, 0, means this is the class third prediction. In which case our resulting class is the third one down, or h theta x3. We can define our set of resulting classes as y. So yi equal to 1, 0, 0, 0 means always your prediction y you don't represent as a class name, you represent as a vector. If it is the class 1, then in the 1th place it is 1. If it is class 2, only second element in this column vector is 1. This is third class, means third value in this column vector will become 1. All others will become zeros. So our final value of our hypothesis for a set of inputs will be one of the elements in Y. For cost function and gradient descent equations, look at the following. You can go through and let's see how the cost function is computed here. But I will try to explain what is the algorithm, how do we fix the weights here. This is called back propagation algorithm. Neural networks, error forward, back propagation algorithm. In simple words, they say propagation, back propagation algorithm. I'll make you to understand what is back propagation. The back propagation equations provide us with a way of computing the gradient of the cost function. Let's explicitly write this out in the form of an algorithm. So usually what happens, let's say to understand without mathematics, how these weights are fixed, because you are fixing weights from first layer to second layer to third layer to fourth, finally you'll get output layer. So we will come to know that whether we are getting accurate results or not. That is based on final output layer. We will compute the final output values and observed values are same or not. If they are deviating, then we need to change weights. Then final output layer is receiving weights only from the previous layer. So it says that, okay, you need to change your weights so that you can come close to the real values. Then the previous layer says that I am not independent. I have got signals from the previous layer. So previous layers also should change their weights, means update their weights so that I come close to you. Then previous layer says that I am not independent. Again, I am getting signal from the previous layer. So the error, whatever is coming at the final output, that is propagated, back propagation, means the error is back, sending back to the previous layer. That previous layer, okay, I can correct some weights, but I cannot correct complete on myself because I am also getting signals. So previous layer also should correct the weights. So that will send again signal that we are not close to the real values. We need to change. That will send that will change weights up to some extent. It also send a signal that previous layer also should to change the weights so that the error, whatever error is coming, that is propagating. Error correction means correct. The previous layer says that the last layer says to the last but one says that last but two. So the corrections is happening from the last layer to the previous layer. That's why this is called error back propagation. Feed forward means when we are computing, the inputs are computed from first layer to last layer. But when we are correcting the errors, we are not correcting errors from the first layer onwards. We are correcting errors from last layer to first layer. So that's why this algorithm is called feed forward, means the computing should happen from first layer to the last layer. Once the computation is done, then we compute the error. Then we want to correct that error. That error is first given to the last layer. That will correct some of the weights. Then it will also suggest the previous layer to correct. So that error is propagating from back to the first layer. So this whole algorithm is called, that's why feed forward back propagation algorithm. So don't confuse that in interviews. They will confuse you that a back propagation means what. Then you shouldn't say that we are computing from last layer to the first layer. No, we are computing from first layer to last layer only, actual values. But only the error is corrected from last layer to the first layer always, the iterations. Means last layer thetas will be computed first based on that previous layer, like that. The back propagation equations provide us with a way of computing the gradient of the cost function. Let's explicitly write this out in the form of an algorithm. So first, what will happen? Input X, set the corresponding activation A1 for the input layer. X1, X2, X3, we are calling A1, A11, A12, A13, like that. To make it, activation in one layer and first and last layer, also to be same notation. We are using even first layer inputs also with A's. Feed forward for each layer 2, 3, because first layer we don't compute anything. For second layer onwards, we start computing from the previous layer. 2, 3L, compute ZL equal to WL AL minus 1, the weights of the previous layer and AL minus 1 plus BL, and AL equal to sigma ZL. So once you get the AL values, convert that to the sigmoid before sending signal to the next layer. So that's why AL equal to sigma of ZL. This sigma is your sigmoid function. So for each layer 2, 3L, compute ZL, WL AL minus 1, weights of layer L based on previous layer inputs AL minus 1. Then this is bias unit BL. And AL, then apply the sigmoid. So then you will get ZLs. ZLs and the next layer activation function. So ALs you will get after applying the sigmoid. So output error delta L, compute the vector delta L equal to gradient of A, C, then sigma L ZL. So then we need to correct the errors. So we need to compute gradients of the last layer, whatever you get, you start computing your gradients based on those weights. Then output error delta L equal to compute the vector delta L. This is the gradient vector. Back propagate the error for each L minus 1. So correction is happening from the last but one layer to the previous layers. L minus 1, L minus 2 to 2. Compute delta L equal to same W of L plus 1 transpose delta of L plus 1 dot sigma L ZL. So from previous thing, you will get delta L, then delta L plus 1, those things. Output, the gradient of the cost function is given by delta C by delta WJKL, AKL minus 1 delta JL, and delta C by delta BJL, that equal to delta JI. So this is mathematically, it may looks like complex. You don't need to worry about this. The basic thing is we are computing from first layer to last layer. Then error is corrected from last layer to the first layer. There are, what are the parameters we are introducing here? Thetas, right? So we need to get gradient descent of those thetas. Then you will get last layer one equation based on some thetas. So we will get gradient descent formulas to correct that. But last layer thetas are computed from the previous layer thetas. So again, you need to go back and correct them. Again, you need to get the gradients for the previous layer, gradients for the previous layer, like that. It's all those things to be updated. So that error will go to the first, then first layer. Once you compute, those again are used to compute the second layer, third layer, fourth layer, like that. It's but it is coming. Okay, you want to change me, but I am computed from the previous layer. Change them. Then first layer starts changing the weights. So once you know the first layer, those are involved in the second layer. Then you use second layer to change the first layer. Then third layer, use second layer, like that. So here it is given, the gradient of the cost function is given by delta C by delta WJKL, AKL minus 1 delta JL, and delta C by delta BJL equal. This is your bias term gradient, and remaining things are coming from the matrix. So this is your neural networks, which we use here. We will discuss more about how to use these neural networks to solve nonlinear problems. The one thing is you should be able to decide how many layers to be taken. That becomes one more input here, parameters. Whether we need to take 3 hidden layers, 2 hidden layers, or 1 hidden layer. Then there are some practical suggestions. They may say that you start with 2 layers, then look your answers. If you are improving by increasing your layers, the accuracy, then you increase the layers. whenever you feel that by increasing the layers, as I told you, you will create lots of features, but your data will become less, that becomes overfitting, then you should stop there, increasing the layers. That is one parameter, increasing the layers. Similarly, increasing the hidden units. In each layer, you may start with some number, like some formula is given, some let's say 3 times, 2 times more than the previous layer units. So you take that, then see that if you increase something like 10% in each layer, are you able to get the more accurate results? If not, then you shouldn't increase. If you are getting more accurate results by increasing the hidden units, you can increase them. So these are all, let's say, trial and error methods. There is no correct formula. Let's say you should have only these many layers. You should have only these many units in each hidden layer. So that's why you need to have some visualization, then see that first layer, when you are increasing the hidden units, is it improving your accuracy or not? If it is not increasing the accuracy, don't increase the hidden units. Similarly, layers. So all those things in our project should be able to show them visually, because we are trying to make them to aware that these are the parameters we are using, and this is the signal what we are getting. If we increase the layers, what is happening? If we increase the hidden units in each layer, what is happening? So those things should be able to provide to the customer, so that they can also feel that we are building the right algorithm, right number of layers and right number of hidden units. So that is what expected when you add this neural network algorithm in your toolbox. As I told you, you can also study, there is one grid search method where you will say that what parameters to be tuned within what range. So that will do, but it takes huge complexity because it has to try many combinations. Neural networks is something like more complex in computing. Once you get the model, then prediction will become in instantaneous. But building model for neural networks, because you are computing so many weights with matrix multiplications and so many iterations, right? Each layer should have iterations to correct weights, then second layer, third layer. So that will take time. So neural networks is a complex algorithm with respect to time. But once we build the model, the prediction purpose, it won't take much time. So when you use the grid search, again, it's that many combinations you will try. So some idea you should have something. So that's why you should study what is the prior experience with other people, what to start, and then how extend we can go. What is the step size? When we are increasing each layer, should be increased one at a time, or we can jump to the double, then can come back to the previous, those things. So that is also important to make a plan that to make it run faster than taking more time. So this is about neural networks. I'll stop it here. You can have more in Andrew Nagy lectures or any other material. But in simple terms, I tried to give you what is neural networks, what is this feed forward back propagation algorithm, why it is called feed forward back propagation algorithm. Okay, if there are any questions, so we can discuss. Otherwise, the class is over, remaining people can leave. I will be there, I will be here another 8 minutes if you have any doubts regarding today's or previous or project, anything. So I'll stop recording.